Good afternoon. Please respond in chat box whether I'm audible or not. Respond in chat box. Yeah. I think this is the last problem we discussed in the previous class. Square root of 1 plus sin x. Let's discuss two more problems in this method and finish off this. Obtain the Maclaurin's expansion of a power x, where a is a constant. Where a is a constant. Obtain the Maclaurin's expansion of a power x. Let's consider y is equal to a power x. Y is equal to a power x. Degree of the expansion is not specified here. Let's expand it up to fourth degree term. Maclaurin series will be y of 0 plus x into y dash of 0 plus x square by 2 factorial into y double dash 0 plus x cube by 3 factorial into y triple dash 0 plus x power 4 divided by 4 factorial into fourth derivative at x is equal to 0. This is expansion up to fourth degree. The function is very simple. Therefore, we shall expand this up to fourth degree. If the function is a little complicated, we just expand up to third degree. Here, to find y of 0, put x is equal to 0. What we get here is y means y of 0 is equal to a power x. X is equal to 0. Therefore, this is equal to a power 0. Any finite quantity raised to 0 is always equal to 1. Therefore, y of 0 is equal to 1. Next, to find y1 or y dash, we differentiate this expression with respect to x. Derivative of y is denoted by y1. And this is a known derivative. Derivative of a power x is a power x into log. This is a known derivative. Derivative of 2 power x is 2 power x into log 2. Similarly, the slide is still in. Is it not moving? Slide? There is some network problem right from morning. Is not moving? Okay. No? Is this moving? Can you see this problem a power x? Okay. Obtain the Maclaurin's expansion of a power x. Maclaurin's expansion of a power x, where a is a constant. Expand up to fourth degree. It is not specified here, but the given function is a very simple function. We can expand up to fourth or fifth degree term. I prefer fourth degree term, so expand up to fourth degree term. Let y is equal to a power x. Put x is equal to 0. When x is equal to 0, y is equal to a power x will be y of 0. X is equal to 0. Y means y of x. X is equal to 0. This is equal to a power x. A is a constant. Therefore, this is equal to a power 0. Any finite quantity raised to 0 is always equal to 1. Therefore, y of 0 is equal to 1. Now we find y dash. To find y dash, we differentiate y with respect to x. Derivative of y is denoted by y1 or y dash. Neither ways you can write that. Derivative of a power x, this is a known derivative. Derivative of a power x is a power x into log a. Next, to find y1 of 0, put x is equal to 0. What we get here is y1 of 0 is equal to y1 of 0 is equal to, this will be a power 0 into log a is as it is. And we know that a power 0 is 1. 1 into log a is log a. 1 into log A is log A. Next, to find y2 or y double dash, we differentiate this expression of y1 with respect to x. Derivative of y1 is y2. This is equal to, now differentiate this. Here log A is a constant, keep it as it is, log A. This log A is a constant, keep it as it is. Derivative of a power x is a power x into log A. Therefore, y2 is equal to a power x into log A into log A is log A whole square. Now put x is equal to 0. What we get here is y2 of 0 is equal to, this will be a power 0 and a power 0 is 1 into log A whole square as it is. Therefore, log A whole square. This is a second derivative. Now we differentiate y2 again with respect to x. Derivative of y2 is y3 is equal to, here log A whole square is a constant, keep it as it is, into derivative of a power x is a power x into log A. Therefore, this is equal to a power x into log A whole square into log A is log A whole cube. Put x is equal to 0. When x is equal to 0, this will be y3 of 0. This is equal to a power 0 is 1 into log A whole cube as it is. Log A whole cube. Similarly, you can find y4 of 0 is equal to, you can guess this, log A whole power 4. Actually, do that, log A whole power 4. Now write the Maclaurin series. Y means a power x. A power x is equal to y naught. Y naught is 1. Y naught or y of 0 is 1 plus x into y dash, and y dash is log A. Therefore, x into log A. Next term is x square divided by 2 factorial into y double dash. Y double dash is log A whole square. Plus x cube divided by 3 factorial into y triple dash. Y triple dash is log A whole cube. Plus next term will be x power 4 divided by 4 factorial into fourth derivative is log A whole power 4. This is the Maclaurin's expansion up to 4th degree term. So please make a note of this. If you have any doubts, you can mention in chat box. This is a simple problem. Next. This is a question paper problem. Expand up to 4 non-zero or 4 non-vanishing terms. X divided by e power x minus 1. This particular problem is a very important problem in examination point of view. Let y is equal to x divided by e power x minus 1. 1 over e power x minus 1 can be written as e power minus into x minus 1. Therefore, x into e power minus into minus plus 1 minus x. X into e power 1 minus x. That's what I have written here. Y is equal to x into e power 1 minus x. Maclaurin series. This is Maclaurin series. First, we find y of 0. To find y of 0, put x is equal to 0. When x is equal to 0, this will be 0. X will be 0 and 0 into anything is 0. Therefore, we get y of 0 is equal to 0. Next. To find y1, we differentiate this expression using product rule with respect to x. First function. Y1 is equal to first function x into derivative of e power 1 minus x is e power 1 minus x itself into derivative of 1 minus x is minus 1. 1 is constant, its derivative must be 0, and that of minus x is minus 1 plus e power 1 minus x into derivative of x with respect to x is 1. Now put x is equal to 0. Put x is equal to 0. When x is equal to 0, y1 will be y1 of 0. Since x is equal to 0, this will be 0 and 0 into anything is 0. This is a plus e power 1 minus 0. That is e power 1. E power 1 means y1 of 0 is equal to e. Next, to find y2, we differentiate this expression with respect to x. Derivative of y1 is y2. Here, minus x is to be treated as first function. Keep it as it is. Derivative of e power 1 minus x is e power 1 minus x as this. Derivative of e power 1 minus x is e power 1 minus x, and that of 1 minus x is minus 1, minus into minus plus. Plus. Derivative of minus x is minus 1 into e power 1 minus x. This differentiation is over. Plus derivative of e power 1 minus x is e power 1 minus x into derivative of 1 minus x is minus 1. Therefore, y2 is equal to, what is common factor here? E power 1 minus x is common in all the terms. You keep it outside. As e power 1 minus x comes outside, what we get within the brackets is x. And here minus 1 minus 1 minus 2. As e power 1 minus x comes outside, we get minus 1, again minus 1. Minus 1 minus 1 is minus 2. And here, as e power 1 minus x comes outside, we get x. That's what I have written here. E power 1 minus x into x minus 2. Now put x is equal to 0. When x is equal to 0, this will be y2 of 0 is equal to e power 1 minus 0 is e into 0 minus 2 is minus 2. Therefore, minus 2 into e. y2 of 0 is minus 2 into. To find y3, we differentiate this expression with respect to x. Derivative of y2 is y3. This is equal to, here e power 1 minus x, this is first function and this is second function. Therefore, e power 1 minus x into derivative of x minus 2 is 1 plus derivative of 1 minus x is e power 1 minus x into minus 1 into x minus 2 as it is. Therefore, this is equal to, here e power 1 minus x is common in both the terms. You keep it outside. As this term comes outside, we get 1. And here, as e power 1 minus x comes outside, we get minus 1 into x minus x. Minus 1 into minus 2 is plus 2. This is equal to e power 1 minus x into 1 plus 2 is 3 minus x. E power 1 minus x into 3 minus x. Put x is equal to 0. These derivatives are required at x is equal to 0. Put x is equal to 0. When x is equal to 0, this will be e power 1 minus 0, that is 1. 3 minus 0 is 3. 3. Next, one more derivative is required because you are asked to expand this series up to first 4 non-zero terms. This is a 0 term, this is non-zero, this is non-zero, this is non-zero. These are first 3 non-zero terms. One more non-zero term is required. Therefore, differentiate this expression again with respect to x. Derivative of y3 is y4. This is equal to e power 1 minus x is first function. Keep it as it is. Derivative of 3 minus x is minus 1. Plus 3 minus x into derivative of e power 1 minus x is e power 1 minus x, and that of 1 minus x is minus 1. Clearly, e power 1 minus x is common factor. Keep it outside. What we get here is minus 1. And here, minus 1 into 3, minus 3. Minus 1 into minus x is plus x. Therefore, this is equal to e power 1 minus x into x minus 4. Put x is equal to 0. When x is equal to 0, this will be y4 of 0. is equal to e power 1 minus 0 is 1 into x minus 4 is just minus 4. Therefore, minus 4. Rest you can do. Substitute in this equation. Maclaurin series up to 4th degree term. Make the substitutions. You can expect one problem from this part in the examination Maclaurin series. It is fixed. Is this clear, this method? If you say yes, we can go to the next method. Okay. This is another problem. Let's do it. Last one. Expand tan pi by 4 plus x up to 4th degree terms. This is also a question paper problem. Expand tan pi by 4 plus x up to 4th degree terms. Let y means y of x. Let y of x is equal to tan pi by 4 plus x. Put x is equal to 0. When x is equal to 0, this will be tan pi by 4, and we know that tan pi by 4 is equal to 1. Y means y of x. Y of x is equal to tan pi by 4 plus x. If you put x is equal to 0, this will be y of 0. This is equal to tan pi by 4. And we know that tan pi by 4 or 45 degrees is equal to 1. Therefore, y of 0 is equal to 1. To find y1, we differentiate this expression of y with respect to x. Derivative of y is denoted by y1. This is equal to derivative of tan pi by 4 plus x. Derivative of tan theta with respect to theta is secant square theta. Similarly, derivative of tan pi by 4 plus x is secant square pi by 4 plus x into derivative of pi by 4 plus x. Pi by 4 is a constant, its derivative will be 0, and derivative of x is 1. Therefore, y1 is equal to secant square theta can be written as 1 plus tan square theta. Therefore, 1 plus tan square pi by 4 plus x. To make the problem simple, we can simplify this. Therefore, y1 is equal to 1 plus tan pi by 4 plus x whole square. And tan pi by 4 plus x is denoted by y. Therefore, this is y square. Y1 is equal to 1 plus y square. That's what I have written here. Now put x is equal to 0. When x is equal to 0, this will be y1 of 0. This is equal to 1 plus y square. Y is equal to 1. 1 square is again 1. 1 plus 1 is 2. Y1 of 0 is equal to 2. Rest is simple. Again differentiate. Derivative of y1 is y2. Here 1 is a constant, its derivative must be 0, and derivative of y square is 2y into derivative of y with respect to x is dy by dx or y1. That is 2y into y1. Put x is equal to 0. When x is equal to 0, y2 will be y2 of 0. This is equal to 2y y1. 2y, y is 1. Into y1, y1 is 2. Therefore, 2 into 1 into 2 is 4. Y2 of 0 is equal to 4. Now we find y3. To find y3, differentiate y2. Here 2 is a constant, keep it outside, or you can treat 2y as first function. I keep this 2 outside. Y into derivative of y1 is y2 plus y1 into derivative of y is y1. Y1 into y1 is y1 square. 2 into y2 plus y1 square. Now put x is equal to 0. When x is equal to 0, y3 will be y3 of 0. This is equal to 2 into y into y2. Y is 1 and y2 is y is 1 and y2 is 4. Plus y1 square. Y1 is 2. Therefore, y1 square is 4. 4 plus 4 is 8. 8 into 2 is 16. This is 16. Y3 of 0 is equal to 16. Next, to find y4, we differentiate this expression of y3 with respect to x. Derivative of y3 is y4 is equal to 2 is kept outside. Y into y2, use product rule. Y into derivative of y2 is y3 plus derivative of y is y1 into y2 as it is plus derivative of y1 square is 2y1 into derivative of y1 is y2. Therefore, this is equal to 2 into y into y3 plus y1 y2 plus 2y1 y2 is 3y1 into y2. Now put x is equal to 0. When x is equal to 0, this will be y4 of 0. This is equal to 2 into y into y3. Y is 2. I'm sorry, y is 1 into y3. Y3 is 16 plus 3 into y1. Y1 is 2 into y2. Y2 is 4. Therefore, this is equal to 2 into 1 into 16 is 16 plus 3 into 2, 6. 6 into 4 is 24. Therefore, this is equal to 2 into 16 plus 24 is 40. 2 into 40 is 80. Now write the series. Write Maclaurin's series up to 4th degree. This is one part of this module. Next, we move to indeterminate forms. This is second part of model. Indeterminate forms. Forms like 0 by 0, infinity by infinity, 0 into infinity, infinity minus infinity, 0 power 0, infinity power 0, and 1 power infinity. Totally, there are 7 indeterminate forms. These forms are called indeterminate forms. 0 by 0, infinity by infinity, 0 into infinity, infinity minus infinity, 0 power 0, infinity power 0, 1 power infinity are called indeterminate forms. In our syllabus, these 3 methods are included. These 3 indeterminate forms are included: 0 power 0, infinity power 0, and 1 power infinity. L hospital server. Only statement is included in the syllabus, no proof is required. If f of x and g of x are 2 functions of x, any functions of x, f of x and g of x are 2 functions of x, such that limit x tends to a, f of x is equal to 0, limit x tends to a, g of x is equal to 0, then limit x tends to a, f of x divided by g of x is limit x tends to a, f dash x divided by g dash f. F dash x is derivative of f of x and g dash of x is derivative of g of x. Differentiate both numerator and separate denominator separately without applying quotient term. For example, limit x tends to a is 0. F of x is 2x divided by g of x is sin x. What is the indeterminate form? As x tends to 0, numerator will be 2 into 0, 0 divided by sin 0 is 0. Therefore, this takes 0 by 0 form. In such cases, we differentiate both numerator and denominator separately with respect to x without applying quotient rule. You differentiate this numerator separately, this denominator separately. Derivative of 2x is just 2 divided by derivative of sin x is cos x. Quotient rule is not applied here. Numerator is differentiated separately, denominator is differentiated separately. Now apply limits. As x tends to 0, 2 remains 2. It is a constant. And cos 0 is 1. This is equal to 2. This is the statement. If f of x and g of x are functions such that the limit f of x tends to 0, limit g of x tends to 0, then limit f of x divided by g of x is equal to limit f dash x divided by g dash x. This is also applicable when the indeterminate form is infinity by infinity also. See this, the L'Hospital's rule can also be employed to evaluate limit x tends to a, f of x divided by g of x in the case where f of x tends to plus or minus infinity, g of x tends to plus or minus infinity. That means L'Hospital's rule is applicable only in two cases. If the indeterminate form is either 0 by 0 or infinity by infinity. In all these cases, we cannot apply L'Hospital's rule. If the indeterminate form is either 0 by 0 or infinity by infinity, then only we use L'Hospital's rule. You make a note of this. Problem. Evaluate limit x tends to 1, x power 1 divided by 1 minus x. Limit x tends to 1, x power 1 divided by 1 minus x. Mark your attendance along with your admission number. Otherwise, your attendance will not be taken as present. Mark your attendance now. You type your name along with admission number. Let this limit be L. You take L is equal to limit x tends to 1, x power 1 divided by 1 minus x. First, identify the indeterminate form. What kind of indeterminate is this? I've taken this limit as L. Try to identify the indeterminate form. As x tends to 1, this base will be 1. And the index will be 1 divided by 1 minus 1. 1 minus 1 is 0. And 1 by 0 is infinity. Therefore, this takes 1 power infinity form. Let L is equal to limit x tends to 1, x power 1 divided by 1 minus x. As x tends to 1, this base will be 1 and index will be 1 divided by 1 minus 1 is 0. Therefore, 1 to the power 1 by 0 is infinity. Therefore, it takes 1 power infinity form. Can we use L'Hospital's rule? No. L'Hospital's rule is applicable only when the indeterminate form is either 0 by 0 or infinity by infinity. We cannot use L'Hospital's rule. Therefore, we shall rewrite this expression or this limit. Take log on both sides. Log L is equal to limit x tends to 1 log x power 1 divided by 1 minus x. Log x power 1 divided by 1 minus x. It is like this. That means this takes log m power n form. Log m power n can also be written as n log m. Therefore, this can be written as 1 by x into log x. Log m power n is n log m. 1 by x into log x, or you can write it as log x divided by 1 minus x. Log x divided by 1 minus x. Log x power 1 divided by 1 minus x is 1 divided by 1 minus x into log x, because log m power n is n log m. Therefore, log x divided by 1 minus x. Now apply the indeterminate, now apply the limits. As x tends to 1, this numerator will be log 1, and log 1 is 0, divided by, as x tends to 1, denominator will be 1 minus 1, and 1 minus 1 is 0 by 0 form. Now we can use L'Hospital's rule. If the indeterminate form is either 0 by 0 or infinity by infinity, then only we use L'Hospital's rule. Now it takes 0 by 0 form, therefore we can use L'Hospital's rule. Therefore, log L is equal to limit x tends to 1, differentiate numerator separately, denominator separately. Derivative of log x is 1 by x, and derivative of 1 minus x is minus 1. Apply limits. As x tends to 1, numerator will be 1 by 1, and 1 by 1 is 1, divided by denominator is minus 1. 1 divided by minus 1 is minus 1. What we get here is log L is equal to minus 1, and required is just L. Therefore, L is equal to e power minus 1. E power minus 1 is 1 divided by. To make a note of this. If you have any doubts, you can mention in chat box. Okay, we'll do it again. Limit x tends to 1, x power 1 divided by 1 minus x. The given problem, you take it as L. Limit L is equal to limit x tends to 1, x power 1 divided by 1 minus x. First, try to identify the indeterminate form as x tends to 1. See, as x tends to 1, this base will be 1, x is equal to 1. Wherever there is x, you put x is equal to 1. Index will be 1 divided by 1 minus x, x is equal to 1. Therefore, this is 1 to the power 1 by 0. 1 minus 1 is 0. 1 to the power 1 by 0 is infinity. 1 power infinity form. This is an indeterminate form. But we cannot use L'Hospital's rule. L'Hospital rule is applicable only in these two cases, 0 by 0 and infinity by infinity. In other cases, we cannot apply L'Hospital's rule. Therefore, we cannot use L'Hospital's rule here. To apply L'Hospital's rule, we must rewrite this function and change the function either to this form or this form. For that purpose, take log on both sides. Log L is equal to limit x tends to 1, log x power 1 divided by 1 minus x. Log is applied on both sides. Log L is equal to limit x tends to 1, log x power 1 divided by 1 minus x. Clearly, this takes log m power n form. Correct? Log, this is m and this index is n. Log m power n is n log m. Therefore, this can be written as limit x tends to 1, log x power 1 divided by 1 minus x can be written as n. This is n into log m, log x. This is m and this is n. Therefore, 1 divided by 1 minus x into log x means log x divided by 1 minus x. Now apply limits. As x tends to 1, log 1. Log 1 is 0 divided by, as x tends to 1, 1 minus 1. 1 minus 1 is also 0. Therefore, this takes 0 by 0 form. Now we can use L'Hospital's rule. L'Hospital's rule means differentiate both numerator and denominator separately with respect to x without applying quotient rule. Therefore, this is equal to, that means log L is equal to limit x tends to 1, derivative of log x. We know derivative of log x is 1 by x. Derivative of 1 minus x, 1 is constant, its derivative is 0, minus derivative of x is 1, that means minus 1. Now apply limits. As x tends to 1, this is 1 by 1. 1 by 1 is 1, divided by denominator is minus 1. 1 divided by minus 1 is minus 1. We get log L is equal to minus 1. Therefore, L is equal to e power minus 1. E power minus 1 is 1 divided by. Is this clear? Is this clear? Those who ask to explain once again, respond. Okay. And for first internals, prepare yourselves, complete first module. I shared the syllabus the day before yesterday. First module complete. And from this second module, yeah, in MACLAURIN'S series. From second module, MACLAURIN'S series. First module, full. You prepare yourselves, complete first module, and from the second module, MACLAURIN'S series only. Okay, thank you.